Hi, this is Good Design Practices Part 3. In the last session, we learned that why we should use synchronized input output for our FPGA designs and how to synchronize them. We understand pipelining concept and we learned where to use them and how it can improve your operating frequency of your designs. Now we will understand asynchronous inputs. We will know that what are asynchronous inputs and why you should avoid using them in your FPGA design. And most importantly, how you can synchronize these asynchronous input before using them in your designs. We will learn about two-stage synchronizations. We will talk about cross-clock domains and synchronize reset de-assertion. So let's start. So we knows that our FPGA designs has some input ports going into the FPGA and some output ports coming from the FPGA. Out of these input outputs, we have to be very careful on asynchronous inputs. Asynchronous inputs are the inputs which can change their state at any time, just like a push button switch or RS-232 signals. These signals are not driven from a clock. So if you use them directly in your FPGA, then your designs can malfunction. So the solution is that we can synchronize all of our asynchronous input. Let's look at this simple example. We have asynchronous input named as X async and we want to synchronize this input, right? So we pass this input through a two flip-flop inside the FPGA. And now output of second flip-flop is synchronized to our clock signal. And it is ready to use now by rest of your FPGA design without any timing issue. This is called two-stage synchronizing chain because it uses two flip-flops to synchronize your asynchronous input. It is important to note that you should not have any combination logic between these two flip-flops. So this is the VHDL code for this. We are needing a registered process block to implement two flip-flop. So we have two signals, temp and xsync. Temp is the output of first flip-flop and xsync is the output of second flip-flop. So at the first rising edge of clock, your asynchronous input will pass through the first flip-flop. It has signal temp here. Now at the second rising edge, this temp signal will pass through to the second flip-flop and you will get X sync output. So this X sync signal is now synchronized with our system clock. And now you can use this signal as an input for rest of your design. Means you turn your asynchronous input into a synchronized input, right? Now let's talk about cross clock domains. This is little complex topic. So we are explaining some basics first. So the problem comes when you are working with two different clock signals in your designs because one clock domain is generally asynchronous to the other clock domain. Means if you sync your signals with one clock signal, then they will probably asynchronized with the another clock signal. So you need to find a way to sync that signal with both of your clock signals. If you have just one clock signal in your design, then there is no need of cross clock domain. So let's see how to do cross clock domain. Well, there are a couple of ways to do so. The simplest way is to use two flip-flop synchronizing chain, as we have seen in the last slide. Another way is to use additional signal for handshaking. For example, you can generate additional ready and acknowledge signal for handshaking between two different clock signals or between two different clock domains. When you have more data such as wide data bus cross clock domains, then you can use dual clock by force to cross the clock domain safely. Next step is use of generics. So try to use generics as much as possible in your designs. This will help you to reconfigure modules very easily and hence you can reuse your VHDL modules in different designs with very small changes. Means you can write your designs with lesser code and also lesser mistakes and it can save you a lot of time because now you have reduced your code redundancy. Means now you are not writing code for your whole design. You are just using your previously developed modules in your code and they are already tested. Means you do not need to test those sections of code. So your time is saved in testing and debugging as well. Next good practice is that always reset all the outputs of your synchronous process. Means always use a register process with a reset signal. Generally, this reset signal is applied when powering up your FPGA, and this is external from the FPGA. Now, when we talk about external reset signals, means outside from the FPGA, then it is recommended to synchronize reset de-assertion. Why? Because these are external reset, like coming from some kind of a reset switch. Means these are asynchronous in nature or asynchronous input. So we must synchronize it to avoid any potential timing issues like we discussed earlier. And if you try to use asynchronous reset signals, then different sections of your FPGA will trigger the reset at different time because of routing delay. And this is not good because some registers inside the FPGA may already complete the reset process, but some sections may still in resetting process. So in such cases, some part of your design may lag by one cycle and some may lead by one cycle. And this is enough to malfunction your design. Means your designs may be not a reliable design. So this is a simple way to synchronize your reset signal. We used two flip-flop synchronizing chain. Output of first flip-flop is temp signal and output of second flip-flop is synchronized reset signal named as reset out. First flip-flop has input 0 at this time. Reset input mentioned by the red color and connected to the asynchronous preset pin of both the flip-flop. And output of this system is reset out. And this signal is now synchronized reset signal. And this can be used now to reset rest of your FPGA design. So when this reset input signal goes high, your reset output will also go high and that will reset your whole FPGA design at once. And when this reset input signal goes low, then your reset output signal will also return to 0, but only after 2 clock cycles. Means your FPGA will come out from reset after 2 clock cycle when reset is asserted. So this is a simple VHDL code for this circuit. We have used registered process block means clock and reset input is in the sensitivity list. So when reset is applied means reset in is equals to 1, then output of both flip-flops are set to 1 means temp is 1 and reset out is 1. Now if reset is not given, then at the rising edge of clock we moved 0 to the temp signal and then this temp output moved to the reset out. Now it's the time for some important notes on clock and reset signal. So we should always try to use global nets in FPGA when routing clock and reset. These are high speed nets and have very low delays. Means these signals can reach to all the registers inside the FPGA in almost same time. This is very important. Modern FPGA tools are smart enough to assign these global nets for your reset and clock signals from your VHDL code. So you do not have to worry about this. Next is always use PLL to clean up input clock signal, even if you are not changing your input clock frequency. Because in real hardware, there are many type of noises. And because of these noises, sometimes single rising edge of clock appears like two rising edges. And this can give unreliable results in some scenarios. So these PLL or phase lock loop can help you to eliminate these type of problems caused by some noises because PLL are having low pass characteristics. So quick summary, remember that always synchronize all of your asynchronous input by using two flip-flop synchronizing chain, including reset signal as well. Always consider cross clock domain problem when you are working with two separate clock signals. We have seen how to minimize this clock domain problem in the 12 clock crossing. These are important to design like this. If you want to use your modules and designs in wide set of applications, means by using this approach, you can reuse your modules for different projects without worrying about different kind of issues which we have discussed. Next, try to use generics in your designs so that you can use them for wider applications. Always initialize your designs and signals using a reset signal. Use global nets to route, clock, and reset signals. Use PLL to clean up all of your input clock signals. So, these are some tips and tricks for good VHDL and FPGA designs. Try to apply them as much as possible in your practices. In the next session, we will do a simple project using LEDs and shift register. So stay tuned for the update. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.